Hello everyone, it's good morning and good afternoon. Myself Richa, and this is a technical session 7B, and this session will be moderated by me. On the behalf of the Global Knowledge Research Foundation, it's my great pleasure to welcome you to the 6th World Conference on Smart Trend in System Security and Sustainability. I hope you will enjoy the knowledgeful and interactive session through the day. In this session, we have a 6 paper presentations, which means in this session we have a 6 to 7 papers, and they will be given 15 minutes for presentation, which means a 12-minute for presentation and 3 minutes for question answer. And there is a another request to all the participants: please stay connected with us till the closing remarks, so we can take a one quick snapshot, so making this virtual conference more memorable. If you have any query and any updates, write it down to chat box. And just before we get started, I would like to introduce our chair of this session, Professor M. Shamim Kezer.
Hello, Richa.
Hello, sir. Dr. M. Shamim Kezer is currently working as a professor at the Institute of Information Technology of Jahangirnagar University, Dhaka, Bangladesh. He is an associate editor of the Cognitive Computation and IEEE Access Journals, guest editor of Brain Informatics Journals and Cognitive Computational Journals. Dr. Kezer is a life member of Bangladesh Electronic Society, Bangladesh Physical Society, and he's also a senior member of IEEE. Welcome to you, sir. And now moving ahead, now we can start with our papers. Now I would like to call our first presenter to present his paper on IoT smart irrigation system for precision agriculture.
Welcome everybody. Can I share my screen?
Yes, please.
Yes. Okay. Welcome. I welcome you all. Good morning, good afternoon. My name is Jawad. I'm from Palestine, and I am studying at Al-Quds University in Jerusalem in Computer Science Master Program. I will be presenting this paper by the title IoT Smart Irrigation System for Precision Agriculture. For introduction, I will start with the fact that agriculture is one of the main resources of income in the economy. One of the key components in agriculture system, agriculture system, is its irrigation system. The efficiency and practicality of the irrigation system will have a direct impact on crops yield. One of the main challenges for an irrigation system is water scarcity. Another challenge is time. Based on the used irrigation system, the task of watering the field could be labor-intensive and time-consuming. To maximize crop yield, farmers must practice precision agriculture, and that is another challenge. A smart irrigation system is part of the solution to practice precision agriculture and thereby getting the most from what resources are available. This paper presents a smart irrigation system that addresses the three mentioned challenges to pave the way for the solution to precision agriculture. Precision agriculture is the future of agriculture. One of the main goals of precision agriculture is to utilize the available resources to its max with minimum resource wastage. The main objective for this system, first, using IoT technologies to automate the irrigation process and save farmers time and money spent on this process. Second, cut the farmers' spending on water and electricity by managing the available resources with maximum efficiency. and managing the water resources by addressing water scarcity without impacting the crop health. And finally, maintain the farmers up to date with the fields and the crops real-time status. An overview of the system, of the general system agriculture is showing in this figure. In the proposed system, there are one main station and multiple control and sensory station. The main station consists of a main controller. We used here Raspberry Pi board and the power supply. The main station receives data input from the sensory stations and the weather forecast API and users direct control from the user portal. The main board output control signal to the field control station and update the field status on the user portal. The system utilizes a wireless connection using Zigbee to connect the sensory, tank, and control station to the main station. And the main board is connected to the local networking using Wi-Fi to provide the user portal and to connect to the weather forecast API. The system utilizes an Arduino Uno microcontroller as the board for the sensory stations that receive measurement reading from the sensors, moisture, rain, humidity, and temperature sensors as data input and output those measurements to the main board. It receives power from the solar panel kit that is directly connected to the board. The control station consists of a microcontroller and a relay. The Arduino board connects to the main station and receive input from the main station as command signals to control the relay that controls the water pump. The water tank station consists of a microcontroller and an ultrasonic sensor, and the tank station sends the tank's water level as input to the main station. As for the methodology, the proposed methodology will be presented as two stages. The first stage, when the system starts, and the second stage is the irrigation process. First, the first stage, the initiation process is presented in this figure. In the system initiation stage, the system will load the crops and field reference metrics that will be used in the decision-making process. Then the system will check for users' update on those metrics. The user will be able to change the field's layout and crops types and their reference value. If there is no update to the reference metrics value, the system will proceed with the irrigation process. In the next stage, the system will start the irrigation process as presented in the following figures. The process will start with the water pump status is off, and if it's a startup process, the system will proceed to the next stage without entering the sleep status. Else, if it's a user direct control to turn off the water pump, the system will adjust the sleep timer based on user configuration. Else, if the system control to turn the water pump off, it will proceed to the next stage without updating the sleep timer. In the next stage, the system will acquire the sensory data from the field sensory stations and water tank station. Then the system will adjust the irrigation time depends on the water levels. Then the system will check the rain sensor, and based on its readings, it will decide whether to restart the process or to proceed to the next step. In the next step, the system will fetch the weather forecast by connecting weather forecast service API and will use the elements of the rain chance and compare it to the threshold value and decides whether to continue the process or restart it. In the next step, the system will compare the reading from the moisture sensors and compare them to the threshold values and decides to proceed to the next step or restart the process. Next, the system does the same for temperature, humidity, sensors readings as well. And if it passes all these steps, the above steps, the system will turn the water pump on for a certain amount of time that depends mainly on the water level in the tank and the sensory data from the sensory station. If the system receives a direct control to turn the water pump on, it will do so for a specific time set by the user. After a change in the system status, the user portal get updated with the new values. In future improvement of the proposed model, we can address system software and hardware security in more details. In this paper, we address some software security aspects such as using ZigBee for wireless communication and its support for encryption, using HTTPS and supporting authentication and authorization for user portal access, and the use for updatable software packages. Integration smart fertilization along with smart irrigation by sensing the chemicals in the soil. This will be for future. And generating and using plant database that include crops, waters, and fertilization needs at different stages of the plant's life cycle. In conclusion, we conclude that the quality and efficiency of the irrigation system in agriculture is a key factor to the success of crops. Water scarcity, desertifications, and food shortages in many areas in the world has made precision agriculture a necessity. From that, the idea of a smart irrigation system developed by utilizing new technologies in the field of IoT and new technologies in the field of agriculture to reach the goal of precision agriculture. This paper presents a model of a smart irrigation system that supports different fields and different crops. The system beneficial in reducing water wastages, keeping the crop in optimal condition, reducing the need for manpower, save times, and always keeps the farmer aware of the farm conditions. And thank you all for listening, and I'm open to any questions.
Thank you, Jawad. I have a question. I mean, if we move towards the system architecture, we have seen you have used moisture sensor, rain sensor, temperature, as well as humidity sensor, right?
Yes.
And also you are collecting weather forecast data using API, right?
You're right.
So weather forecast data is already giving you temperature, humidity, and rainfall information of a particular location. So why we need this sensor? A moisture sensor is okay because you are using, I mean, the based on the moisture condition in the soil, you are, doing the irrigation, right? But the other sensor information you are getting from the weather forecast. So why we need this?
It's true. I use the the temperature and humidity sensor in the sensory stations and not really relying on the data from the API, because in the weather forecasting may not be as accurate as the in field physically, physically being in the field and sensoring the humidity, the temperature, if in the field, when the water evaporates, humidity will be not as the same as the weather forecast. It will be higher humidity. The temperature may get down, not be the same as the getting data from the weather forecast. From the weather forecast, mainly I rely on the rain chance. So if there is rain in the next hour with some percentage, the system will not start the irrigation system. It will wait until the rain started and it will do the job. I hope I answered the question.
Okay, thank you so much. And also you are planning to use, the soil sensor, soil nutrient sensor in future, right?
In the future, yeah, the chemicals of the soil will detect if it's need fertilization. There's no need. It's a future work. I'm implementing on version 2 of this research.
Okay, thank you so much.
Thank you.
Now we can call our next presenter to present his paper on blockchain security and calculation improvements. Ivalo. The paper presenter name is Ivalo.
Thank you very much. Let me share my screen. I hope you can see my screen, guys.
Yes, it is visible.
Okay, thank you very much. So, let me introduce myself. My name is Untitled Chapter. And I'm going to present
Sorry for interrupt. Actually, your voice is not properly. It's break.
It's broken voice. I mean, yeah, we are getting the broken voice from your microphone.
You're getting what? Can you say it again? You don't hear me or you don't see the screen. Can you tell me, please?
The screen is okay. I think something wrong with your microphone. So we are getting the broken voice.
Okay, give me a second. Let me check.
Anyways, I think you can present.
Yeah, let me try another way with I will
Yeah,
take,
excellent. Excellent. It's working. You're audible properly now.
okay. If something wrong, please let me know and I'll change my headset and or I will use the computer's microphone. Sorry for that, guys. But yeah. Okay, so let me present my paper, which is called Blockchain Security and Calculation Improvements. First, I would like to start with the high-level overview how a blockchain looks like. As we know, it's a chain of different blocks cryptographically linked to each other. So once a block is formed and it's added to this network, it's almost impossible to be changed because the whole blockchain is stored in each of the participating hosts in that network. So we have two types of blocks. One is the genesis, the starting block that is slightly different than the others, and the other normal blocks that contain the transactions, and they have a block header with certain amount of attributes within them. Why the blocks are cryptographically linked? Because once a block is formed, from its header is calculated the hash, which hash value is included into the next block, which is to be added into the blockchain. So a little bit more details around the block structure. It has a block header with certain amounts of attributes, and it has a block body with the transactions included in that block. As I said, the block header contains the attribute, the calculated hash value from the previous block header added into the current block. And also, one very important attribute in it is the so-called Merkle root hash value, which is the calculated hash value from the binary tree from all the transactions participating into the body of that block. It's called Merkle because this it takes the name of its inventor, Ralph Merkle, who invented this tree and this calculation of the hash from all the underneath transactions. A typical transaction calculation of one transaction, if, for example, we have one transaction to be added in a block, looks like this. We have the transaction, we have a computation of the hash value, and because we have just one transaction, then this Merkle root hash value is the calculated hash value from that transaction. For example, in a Bitcoin network, we have this hash function is the so-called double SHA-256, which means once we calculate the hash value from the transaction, we calculate again the hash value from the calculated hash value from that transaction. And that's the reason we call it a double hash calculation. Well, in general, we don't have one transaction in a block, we have more. For example, in this slide, you see 3 transactions calculated in this way. On the first level, we have the leaves of the tree, which are the transactions. We apply on them the hash calculation. So we have hash A, hash B, hash C, calculated values from them. Then on the next level, we have the calculated hash value from the first and from the second calculated values. And at the last level, we have the calculated hash value for the whole tree, which is in this case the Merkle root attribute that is added in the block header. Now, with 4 transactions, more or less nothing new here. But few questions are arising here around the computation of this Merkle root value. Is it possible to speed up this computation time? Well, if it is possible at all, and at the same time, how we can improve the security? The proposed method is dividing the whole computation of the Merkle root block header attribute into 4 groups. I put here to use different hash functions, but they can be the same, or we can use the same functions within the different groups. So we have to play with those grouping of the hash functions within the group. Well, reviewing the possible options, I used arranging the functions into 3 different variants of the different groups. So at the end, I'm comparing the computation time for the classical Merkle root value with the double SHA-256 compared to the 3 variants I propose here in this research. How it looks like the computation of this root with the proposed solution from one transaction. Well, instead of having just one hash computation, which is H1 from the transaction A, they are used 4 different groups, and in general, 4 different hash functions are used. So once we calculate the hash value from the transaction, then we use another hash function, calculate another hash value, and so on up to the level. So 4 different groups with 4 different hash functions. The slide shows if you have 3 transactions. Again, nothing special here compared to the one transaction. And it to be more descriptive, I put this slide to show if you have, for example, 9 transactions that have to be added in a block. Now, at the first level, we have 9 computations of 9 hash values because we have 9 transactions. On the next level, we have 5 different computations using another hash function. Then on the 3rd level, we have another computation, and the level from it above to the top, we have 2 levels, but they're using the same hash function. So with that, because we have just 9 transactions here, but in general, we have many more, tens of thousands. All the transactions that are from level 3 above will be not transactions. So the hash calculations will be calculated with the SHA, with the hash function used for this group 4. The three variants that I'm reviewing here are using the four functions SHA 256, 512, and from the third family, the same functions. Starting from bottom, from the leaves to the top, the first group in first variant is using one function, the second group is using another, third one, and fourth one. The difference here is that in variant 3, I'm using two functions only, and I divided them. I put the slowest one, the fastest one at the bottom, because we have, if you take this diagram, we have the maximum computations here, because we have that number of transactions. So it makes sense to put the fastest possible computation of hash function at the bottom, and so forth to the top. My experimental environment consisted of 6 virtual machines from different types within the Amazon infrastructure, within Microsoft, and within Google cloud infrastructures. Why this? Because they're general. I didn't put any customizations, any performance tuning here. They're just anybody can make a virtual machine from those type, and will get the same environment which I used. I did 50 different tests for sequential computations, having 1K, 10K, 50K, 100K, and 1 million sequential computations over those 18 different type of virtual machines. Finally, I tried to achieve kind of average time for each of the infrastructure vendors, having the time needed for a single computation of hash function. I used single and double calculation because within the example which I used with the Bitcoin, for example, there is used double computation of SHA 256. So it was used for comparison of the results after that. Putting all those information in one chart, you see the things on the slide. I compared the computations of approximately 14,000 transactions. Why? Because I found one statistic for 2019 year. There are something like 441 billion transactions with card done all over the world from the 6 biggest card vendors in the world. So it gives something like 13,988 transactions per second. And the comparison here is to show that, is it possible to with the proposed solution to compute the Merkle root hash value faster than the classical one? And with the proposed 3 variants, you see the dotted blue line here around the circle, which is circling the values that are faster, the computed values that are faster than the classical one. My purpose was not to compare the vendors, but just to see if it is possible at all with having different groups of and using different hash functions to see if we can achieve something better in terms of time calculation. And of course, we achieve security with that because we're using not just one function. We are using, in variant 2, we are using 4. In variant 3, we're using 2 different hash functions. Here are some percentage showing in which variant, which cloud infrastructure gives faster computation time compared to the others. Well, as a final conclusion, this new method is proposed for computing the Merkle root hash value using 4 different groups with different or with the same hash functions for the computations. The 3 variants were reviewed and compared to the classical one. So at the same time, it improves the security because it involves usage of 2 or 4 different functions instead of just 1. And with that, some information about myself. I work in the University of Telecommunications and Post Department of Information Technologies in Bulgaria, Sofia. I have different interests of areas of interest like blockchain security, cloud infrastructures, automation, virtualization, and so on. Yeah, and with that, you see my contacts. If you want, you can get in touch with me via email or via LinkedIn. And with that, thank you very much for your attention. I'm ready for questions or whatever you have.
Thank you, Professor. I mean, for your excellent presentation. I'm curious about, you have mentioned how to speed up the computation time and how at the same time we can improve the security. I mean, so if we improve the security, the computation time will definitely improve, I mean, increase, right? So is there any trade-off between these two?
If we improve the security, the computation time will increase. Not definite. If you see on this slide on the screen, in the first variant where I have 4 different hash functions.
Yeah.
While in the second variant I'm using the same functions but in different order because, for example, SHA-3 256 gives faster
more computation is required, yeah.
Faster computation time compared to SHA-256. So I'm using 4 functions, and if you see in the chart, the second variant is giving me for Microsoft Azure and for Amazon better times than the just double SHA-256. In the same time, here in variant 3, I use just 2 functions, and of course, yeah, they gave even better times in terms of computation. So I would say not definitely improving the security will decrease the computation time because, yeah, I played here with different functions. I cannot compare how strong one of them is compared to the other one, but I just try to play with different functions to see if I can achieve any performance improvement while at the same time having many. Yeah.
Okay, thank you so much. It was the only question. Thank you.
Thank you very much, guys. Any other questions?
Richa.
Yes, sir.
Please move to the next.
So moving, yes, sure, sir. So moving ahead, we can call our next presenter to present his paper on application of deep convolution neural networks, mobile net V2, and exception for detecting cardiac arrhythmia.
Okay, you can hear me? Okay.
Yes.
Can I share my slide? Okay. Okay, let's start it. Good morning and good afternoon and good evening to everyone. My name is Deshanat Akalajaka and I'm from Chiang Mai University in Thailand. Okay, I'm going to talking about my research, the core application of deep convolutional neural network and mobile net V2 exception for detecting cardiac arrhythmia. Okay, gonna outline. We have a introduction. This objective to data information method result.
Dear presenter, can you please speak up louder?
Okay. Okay, can you hear me?
Yeah, I can hear you, but your voice is very low.
Okay. Okay.
Yeah, now this is perfect. It is perfect.
Okay. The last one is the conclusion. Okay, can start with the introduction. Okay, cardiac arrhythmia is the condition in which the heart is not beating in the natural rhythm. It may be reading too fast and too slow and making the pump to different part in the body is not efficient as it should be, and may increase the risk of the heart failure and strokes. Okay, and cardiac arrhythmia is several causes such as a lack of sleep, can intake fatty foods, not exercise, something like that. Okay, and moreover, cardiac arrhythmia remain the leading cause of death worldwide. Mm. Cardiac arrhythmia causes it of the part in EKG, like abnormal in SA and we know abnormal in bladder bunches and abnormal in Purkinje fiber. Okay, object research to detect type of cardiac arrhythmia and to compare accuracy between two CNN models like transfer learning with mobile V2 and transfer learning with exception. Okay, talk about two CNN or convolutional neural network has the advantage of the being able to extract feature for of the feather classification, and CNN is suitable for leading to picture recognition. Okay, next one. Traveling with mobile V2 is a small model with a fast processing, low latency, and a low computing power. It is designed for result constraint time. And mobile is very good for classification, detection, and segmentation data or the data set. Okay. The happening with the exception is a has had a compute layer, and the exception is the simplified architecture by dividing the computation into three steps for optimizing the processing efficiency, like empty flow, middle flow, and exit flow. Okay. Next, we're gonna talking about data information. Okay, the data that we use in this research is called EKG or electrocardiogram, and EKG is the graph that shows how the work of the electro pulse generated by the heart to pump the blood supply the body. And EKG that we invest in is divided into three parts, like SA node, SA and EV node, blood bunches, and Purkinje fiber. Okay, in this picture, it shows about how to work for each part of heart. Okay, and SA and EV node is work together for generator electrical. Okay, next one. The data that we use is image with the format size of the 128 by 528 pixel, and we take from the partial bank ATM. For training, okay, we divide the data into four cassettes, like abnormal in the SA and AV node, abnormal in bladder band size, more in the Purkinje fiber, and normal condition. Okay, this one is show about one of the sample in the abnormal in the SA and AV node cost. Okay, this one is show about yes about abnormal in bladder band size cost. Okay, and this one is the abnormal in Purkinje fiber, and this one normal condition. Okay, next one method. Okay, we start with the four type of EKG sample from the partial bank ATM and 2000 images per card, and total of the 10,000 images. Okay, next step, just filtering of the images and eliminate it. Okay, next step, just adapt the size of EKG sample to the 120 multiple 120 pixel and reduce the unwanted data by adapt it into the black and white color. Okay, next step is design and develop both CNN architecture like happening with mobile net V2 and happening with exception. Okay, and next step is just divide the EKG sample into the 70% for training set and 30% for validation set. Okay, this picture is show about the number of each set. And next step is just train the data and test the data. Okay, after that, we just get the result. Okay, we just focus on the accuracy. The mobile net issue gave the 98.58%, and in the other hand, exception model gave the 94.51%. Okay, in the future, we try for medical use and design and develop the program to easy to use in development. Okay, in conclusion, okay, this research choose in model to classification type of cardiac arrhythmia and compare the accuracy. And this research used EKG data from the partial bank ATM, and we divide the data into 4 classes, like abnormal in SA and venous, abnormal in bladder bulges, abnormal in Purkinje fiber, and normal condition. Okay, final. Based on experimental results, we found that hyperlearning with the mobile V2 achieve higher accuracy than happen with the exception model, along with better capacity and the kappa score and better cause entropy loss. Okay, thank you for your attention.
Thank you, Chaitanya. I have only one question. I mean, you have used, MobileNet 2 as well for this purpose, right? For identifying arrhythmia.
Yeah.
So I mean, why you have chosen this model? There are other transfer learning models as well. What is the rationale behind choosing this model?
Because I want to know about the result about 2 models to compare. And in my university, and I'm studying in the first year in the university, and I have many questions about 2 models, and I just do it.
Okay. Have you done the parameter optimization or parameter tuning for these models for the chosen data set?
I cannot hear you. Can you?
Have you done the parameter optimization for the model you have chosen? Have you done the tuning of the parameter?
I'm just training the data.
Okay, so you haven't done the parameter tuning anyway. Okay, thank you so much.
Okay, thank you.
So now we are calling our next speaker to present is a paper on estimating nodes number in nano networks using 2 algorithms.
Hello, everyone. Good morning and good afternoon. Can I share my presentation?
Yes, sure.
Okay. My name is Adara Hijani. I'm a lecturer at Al-Nahrain University in Baghdad. My paper is talking about estimating the number of nodes in a nano network using 2 algorithms. In this presentation, I will try to explain the significance of network size Then I will give some background about the nano networks, how small is nano, and how and what are the communication techniques used in nano networks. Then I will talk briefly about the proposed algorithms, which are based on two concepts. The first algorithm is based on Aquarium Sensing, which is a biological concept that is used among bacteria. So it's based on biological concept. The other one is based on beeping model. Actually, this algorithm is adapted from an algorithm that has been applied on beeping model. So at the beginning, what are the significance of network size? It's important to know the number of nodes in a network because it can help or it can be used to maintain the tune or rates which the topology is maintained. It can help in choosing the level to determine the outgoing links and designing algorithms that adapt their actions depending on the system size. So it's important to know the number of nodes of any network. So we'll try to understand how small is nano. Nano is from a Greek word, which means dwarf, that it's too small. Actually, there is a web page called htwins.net. It starts from the size of the universe and go to beyond the size of cells. And for example, here the red blood cell and the cell nucleus, it's go beyond that size. And we can see that even it's 10 to minus 5.2, it's not the size of nano. The size of nano is less than the size of red blood cell. It's almost 10 to the power minus 9. So here we can see that the nanometer can be 10 to the minus 9. So when we are talking about nano networks, we are imagining very, very small devices or nodes that are communicating between each other. So nano networks is related to nanotechnology. Nanotechnology is becoming a key area in science based on multidisciplinary collaboration among medicine, engineering, physics, biology, computing, and other disciplines. It's promising new solutions for different applications. For example, the advanced health monitoring, drug delivery systems. So it's combination, it's combined different science to solve different related problems. We can consider the basic functional unit in any in nanotechnology is nanomachine. A nanomachine can perform simple tasks like sensing, actuation. But if we have number of nanomachines and these nanomachines are communicating between each other and interacting between each other and share information between each other, they can perform more complex tasks and achieve more important or solve more complex problems. And by communicating and sharing information, they would form a nano network. So a nano network is number of nanomachines that are communicating between each other, forming a network of these nano devices. The main challenge in nano network is how to make them communicating between each other. Actually, when we think about the communication, I mean the conventional network, the use of the metallic antenna will not be feasible in nano network because that will induce high resonant frequency and huge channel attenuation, making the transmission rate almost reach 0. So it's not feasible to use the metallic antenna and apply it to nano networks. So when we think about nano network, this is just a symbolic representation of nano network. Does not equal a miniaturization of the conventional network. So it's quite different. It's not merely downscaled version of the conventional network. So the communication techniques which are used in nano networks, there's a called nano electromagnetic communication. So to overcome the limitation of the electromagnetic use of nano network, graphene based nano electromagnetic antenna have been proposed. That would would reduce the attenuation and help. I mean, it make the communication feasible between nano machines. The other type of communication, which is most common, is molecular communication. Is the communication that are used between cells in human body. Because thinking about that, these nano devices are in size are quite close in the size of cell. So it's been this research been studied the cells and how they are communicating between each other, trying to apply these communication techniques to nano devices. There are different communication techniques. In molecular communication, there are diffusion, calcium signaling, molecular motors. Each one of them has a biological background. Each one of them has its advantages. Each one of them have some drawbacks. So in this paper, we are basically the nano network that proposed in this paper is supposed to use diffusion-based molecular communication. So the molecular communication is a promising way to achieve communication between nano devices where information is encoded as molecules. So So here's an example of the diffusion-based nano network, imagining that there is a nano machine number 1, which is the transmitter, and a nano machine number 2, which is the receiver. And these are the molecules that are sending the information to the receiver. So these nano machines, when are propagated into the environment, they would go through random walk according to the random walk law to reach from higher density into low density to reach to the receiver nano machine. So we can consider it as this. The channel consists of transmitter, and there's a signal that is transmitted, which represents the molecules, and the molecules are transferred through a channel to reach to the receiver, sending it a certain message. So coming to the algorithms that proposed to count the number of nanomachines in a nano network. As I said, the first one is based on Aquarium Sensing, which is a biological process. This biological process is used between bacteria. It helps them to communicate. It helps them to synchronize their performance. The concept of Aquarium Sensing is that these devices, if we apply to the nano network, will emit a certain type of molecule. It's called autoinducer. Emit this autoinducer and receive that autoinducer. So the concentration of this auto-inducer molecules in the environment will increase proportionally as the population, for example, the bacteria, will grow. So if we have number of nanomachines in the environment, in the network is higher, so the auto-inducer or that certain type of molecule will also increase. Bacteria are able to sense their cell population density using this concept of aquarium sensing. So it's a powerful tool to coordinate the courses of actions of nanomachines. It can help to achieve global synchronization by means of molecular communication in a fully distributed manner. So for example, if we have number of nanomachines that are in the environment, each of these nanomachines will release synchronization molecules or auto-inducer. We calculate the aggregate concentration of molecules as sum of the concentration of the group X. So we can compute the concentration of the synchronization molecules in the environment and the amount of emission molecules by each node at each time, and dividing it will give us approximate number of nanomachines in the environment. So the time estimation of the number of nanomachines is inversely proportional to the amount of diffused molecules by each nanomachine. Eventually, the size it will be inversely proportional to the size of nano network. The second algorithm is based on beeping model. Beeping model is quite, the concept of beeping model is quite similar to diffusion. So we have a group of nodes that are communicating through multiple access channels. The communication concept of beeping and listening to the channel is similar to the concept of diffusion-based molecular communication, and that's why we considered adapting beeping model. The algorithm is consists of 3 slots. It's adapted from this paper. During the first slot, if there's none counted nanomachine, will diffuse a unit U of molecules with a certain probability. We assume the probability would be I over J. To raise the opportunity that a nanomachine diffused alone during the first slot, the algorithm will use an adaptive probability 1 over J. If the value of J is too large, that could possibly mean no nanomachine will diffuse during the first slot. Therefore, we can increase the value of, will decrease the value of J. Else, if not, if the value of J is too small, then it's likely that many nanomachines will diffuse during the first slot. The main point which the algorithm attempts to maintain is that the probability of success is maximum when J equal n hash, which represent the approximate number of nanomachines. In summary, we can say that molecular communication is a promising way to achieve communication between nano devices. Aquarium sensing is a biological mechanism that can be deployed to count the number of nodes, to coordinate and synchronize the nanomachines in a nano network. And the communication concept in beeping model of beeping and listening to the channel is similar to the one in diffused molecular communication. And thank you for listening. If there are any.
Yes, I have only one question.
Yes.
Yes, ma'am.
Yes.
Diffusion-based molecular communication.
Yes.
In case of this kind of communication,
Yeah.
we need to have the higher molecular production rate. Do you think, the diffusion-based molecular communication is, working properly with the limited molecular production rates? Have you checked this one?
My work was mainly in theory, so I'm just doing algorithms, and so I haven't physically done nano devices and apply it. Actually, I have because I need to collaborate with somebody in physics to actually build a nano devices. So mainly my work was in theories based on algorithms and applying these algorithms, run these algorithms as programs and getting results. Unfortunately, I haven't done it.
Okay, thank you.
Yeah, thank you very much. If there are any questions.
Yes, now I'd like to invite our next presenter to present her paper on detection of COVID-19 from X-ray images using machine learning models. The paper presenter is Mahin Islam.
Hello. Good morning and a very good afternoon to everyone. So I am Mahin Islam. So let me present my slide first, share my slide first. Okay, let me introduce myself. So I'm Mahin Islam. So I'm from Bangladesh. Here I'm working in a university in computer science and engineering department. The university is East West University. So the title of our work is Detection of COVID-19 from X-ray images using machine learning models. So this is my presentation outline. So as we all know, so we have all bust rate, that is the coronavirus outbreak took place in 2019 in China, so which actually pose a great threat in public health and global well-being. And the major approaches for detecting COVID-19 are different types of tests, among which some tests are popular: RT-PCR test, gene sequencing of respiratory or blood samples, then chest X-ray, chest CT scans. So all of these approaches, as we have seen, actually was quite expensive and time consuming at the time when the pandemic and was in the worst situation. Like it took us many days to get a serial for getting a test like RT-PCR. And again, to get the result, it took a lot of time. And in case of chest X-ray, as compared to RT-PCR, this is more cost effective, and also it gives more accurate direction of the health condition of a patient, specifically the lung condition. So as we know, the lung infection led to a great damage, and many people actually had died, and lots of people are still suffering. So chest X-ray and CT scan, these were two methods which can actually find the condition of lung. And obviously CT scan gives the more precise or accurate image, but actually CT scan is more expensive, and actually you cannot perform repeated CT scan to a person due to the problem of radiation. So what we thought that okay, so taking X-ray images is more better option than going for the CT scan option. But actually, to evaluate these X-ray images, it takes much time, because we have to give all those images to some experts. They have to take some results. So manually, it takes more time. It takes much time, and during that time, when we need some result very quick, so this actually inspired us of thinking about that if we apply some machine model learning models to predict COVID from the X-ray images, so it would save our time, our money, save our health finally. So here we, in our work, in our research work, we use the convolutional neural network, which is a deep learning technique to actually detect COVID-19 from the chest X-ray images. So uh, basically, here the learning models we have used, it can detect COVID positive cases, negative cases, as well as viral pneumonia cases from the X-ray images. So obviously, our objective is to detect COVID-19 more accurately by reducing the complex task and getting better accuracy. So we have actually used different models, so about which I'm going to discuss next. But before that, already in literature, there are many works. There are many works which have worked on this particular domain, so to identify COVID-19. So from some recent references, our finding is this, that there are many works which have used different approaches on different kind of their obtained accuracies are this. So obviously our motivation was firstly to have a rich data set. We wanted to have a data set with much more data, and we wanted to improve our accuracy. So the data set actually we have used is for identifying three classes: COVID negative, COVID positive, and viral pneumonia. So the total number of images we have used here is more than 7,000. So actually we have collected those images from Kaggle, from Google, and also from some hospitals. So actually we actually collected those images from our personal connections. So actually, as we can see that this is a sample X-ray image. So this is for viral pneumonia, this is for COVID positive patient, and this is for COVID negative patient. So in case of viral pneumonia and COVID positive X-rays, they are very similar kind of. There is a difference, but in order to detect the difference visually, so there is 15 to 20% of difference. So it's difficult to detect is visually, but using the techniques, using the machine learning models, we got better accuracy. So this is the CNN architecture. So the models we have used here is Inception V3, AlexNet V16, and EfficientNet V4. So, so these are the features of Inception V3. So actually it reduces parameters. Instead of using filters, we are using less filter, so which reduces the computational resources. And AlexNet, though this is a kind of old model, but it can work better. We found that it gives good result, good accuracy for limited resource. As it breaks down, it works over, it creates multiple threads and breaks down it work. So actually what happens with limited resource, we can actually get better result. So then we have also used VGG 16, EfficientNet B4. All right. So these are the models we have used. So first, definitely after we did the data normalization, because a picture may come in different sizes, but we needed to convert them into a fixed size, and then before applying to our model. And this is the result of applying different models. So at the training accuracy, we found to be 92%, 99%, 97%, 98%, like this. And also we have validated our models with other data sets. So there we can see also that accuracy is quite good. And these are the accuracy graphs. So actually it took 15 epochs to get to a stable accuracy level. So for every model, but for different model, we got different accuracy levels. So these are the model statistics, confusion metrics for LXNet. So these are the values shown here: precision, recall, FI score, and for BGG16 for inception, for efficient net B3. So this is the summarization we have. So for all the models, we can see for LXNet, in order to label viral pneumonia, this is the precision value, recall value, F1 score, and so on. So altogether, our models performed good in case of efficient net B4, and in case of inception V3, in case of VGG16, we got the better results as compared to other two. So finally, this is the conclusion. So actually, COVID-19 infection is a threat to billions of people till now. It's a threat. So if COVID-19, as we know that the lung infection becomes severe, and chest X-ray is done to detect the level of lung infection. And so as we have seen that using our model, we can identify the classes, COVID positive, negative, viral pneumonia quite efficiently. So this finding shows us that different models can be used, add up considering different parameters, and it will give us the reliable result. And this is actually our future work. So collecting more data, and then we obviously we are very much enthusiastic to compare between different variants of COVID. And finally, our what we actually dream to do is to build a web application or a mobile application using which the doctors can easily detect COVID-19 or give the appropriate treatment using the learning models. So this is all from my side. Thank you, everyone. Thanks for your patience hearing. Thank you.
I have one question, Ms. Maheen.
Yes, sir, please.
I mean, have you done the parameter optimization for your models? Or the parameter tuning, have you done that one?
So actually, for images, we have resized them to bring to a specific size. Other than that, nothing much actually.
So in the pre-processing, you haven't tried the other techniques in the pre-processing phase?
No, actually not. We didn't try the other techniques.
Okay. Have you tried the fusion of different models?
I didn't get the question.
I mean, let's say you have used different transfer learning model, right?
Yes.
And people
yes,
also tried with the fusion of different models, and they claim that they got the more accuracy.
Yes.
So have you tried this kind of thing?
Oh, no, actually, no. We haven't tried the fusion. We actually specifically tried this model. We also tried some other models, but actually, for these 4 models, we got better results. So actually, we didn't try much more.
Do you think, this kind of model can be used in portable device like mobile phone?
So actually, obviously, in order to develop an app using this model, this will be quite difficult because actually it requires a lot of computational power. So still now we are thinking about the web application, but mobile application, maybe we have to do a lot more study. So if we want to think about that.
Thank you so much.
Okay, so thank you, sir. Thank you, everyone.
Thank you so much. Now we are moving forward with our next presentation that is on classification of the DLT consensus algorithms with focus on blockchain. The presenter is Ivailo.
Thank you very much. Sharing my screen. hello everyone again. Just for the protocol, my name is Ivailo Chenchev, and I'm going to present this time my second paper, which has the name of classification of the DOT consensus algorithms for with focus on blockchain. The DOT stands for distributed ledger technology. So I had 3 goals ahead of this research, and just to be honest, I will be shorter than previous time because of the specific of it. The first goal is to discover any specific trends of research interests, if I could. The second goal is to identify some classification criteria, like, for example, the type of the network, like public, private, hybrid, federated, like if there are any layers in it, etc. And the third goal ahead is to classify the existing DOT consensus algorithms with the focus on blockchain, which will be based on the architecture and on the access type of these networks. First was the literature review done in few phases. The first phase, as I called it, identification search criteria, was to identify as many papers as possible from these few companies like IEEE, Digital Explorer, Scientific Direct, ACM, Digital Library, ResearchGate, and so on. I based my search on 14 keywords or phrases, which you see here on the slide. I'm not going to read all of them, but this was used to retrieve papers from those publishers. So finally, I managed to collect 1,370 papers with those keywords. On top of it, the second phase, which I called scan criteria, was extended in terms of keywords and phrases. And on top of those 1,370 papers, was done scan with the 27 keywords which you see on the slide. You see here some phrases with 2 words with a dash in between, like abbreviations like Internet of Things, IoT, for the scan. The case sensitivity was ignored, and also I saw that for some of the papers, for example, smart contract was with a dash in between the words, and within some was without. Decentralized was with Z, and with some was with S. So I scanned the papers, identified differences between the typing of the words and the phrases. Finally, you see in this table top 5 words in terms of occurrences per year, because the different papers were identified throughout the years. All papers identified till 2013 were combined in the first row, because there were very few, and there was no reason to put them in a very big table. So out of this table, you see how many occurrences of those top keywords we have, and also the number of papers mentioning those words. I use this information to see throughout the years what was the trend, what were the interests. Of course, the result is based on the first keywords used to identify the papers, but it was interesting to see throughout the years those few keywords, how they appeared in the papers. On the first chart is presented the occurrences per year of those 2 words, distributed and decentralized. honestly, I was a little bit surprised to see that there was kind of big interest in 2019, and you will see this in the following chart as well, but charts as well. But yeah, that's the result. So I cannot discuss why was that. This is just the result of the scanning. So there was a big interest in 2019 for the other keywords like Bitcoin, Internet of Things or IoT, cryptocurrencies, and fintech. You see the chart here, number of occurrences per year, and a little bit surprisingly, the fintech, the financial technologies, didn't have enough presence in the papers I reviewed. But yeah, okay, that's are the results. Here you see the occurrences per year between the permissioned and permissionless networks, because for example in the blockchain networks we have two types of networks. One type is the permissioned, where we have to be given the access to participate in those networks, and the second big part, the second big part of it is the permissionless, like the Bitcoin, where you don't have to be given the permission to participate in this network. Now, finally, the occurrences per year, as you see in the chart, for blockchain, transaction, and consensus. Why? Because yeah, the blockchain is the type of decentralized network, which is yeah, obviously my area of interest. The transaction, because we put the transactions within the blocks, within the blockchains. And the consensus, this is the algorithm that is deciding whether to put a transaction in a block, how to form the block, trusting the participating hosts, and so on and so on. So we see again in 2019 a big interest within the papers. For example, blockchain appears to have times more occurrences than compared to the other keywords. Within the papers, I managed to find some partial classifications, and one of those is to divide the consensus algorithms into two types. The first one is competitive algorithms. The second one is the collaborative algorithms. But this was just a partial, I would say, because it has just few different algorithms pointed there. Well, throughout the papers, I managed to see different reviews, tens of thousands of surveys, literature surveys, but yeah, to me, I missed the classifications. So that was the goal which I put ahead, to try to classify those algorithms with the focus on blockchain. First, on top of the classification stands the distributed ledger technology, and I managed to discover that it has two types of depending on the construction, fuel, and depending on the type of access. We have the permissioned and the permissionless networks. Depending on the construction type, one of the networks is the blockchain, which is the decentralized systems around it. First, big classification based on the decision type. Let me extend a little bit. I'm not sure you can see this. Yeah. I'm not going to read each of the algorithms here, but this is the part that I was missing a lot throughout my last few years, to see how those algorithms can be classified, and to see which one is derived and where it stands. Here, from the papers, I managed to identify two big classes. One is the so-called proof-based, where you have to prove that you've done certain amount of work. You've done something to be able to prove that your transaction has to be added into the block. So those algorithms are based on something that needs to be proved by yourself. And the voting based, the second big part, which is slightly different than the proof based, but yeah, it has also a lot of algorithms used there for the final decision to be added to certain transaction or not. The second big classification that I managed to prepare from the papers is for the access type. And yeah, two big parts, the permissionless and permissioned. And again, they are divided into public networks, federated, which are based on a kind of consortium, and the private or hybrid, which are blockchain networks, but they are just around one organization or around few organizations, and yeah, you have to have access to participate in those networks. So here are the names of the used consensus algorithms in those types of blockchain networks based on the access. As a final conclusion, yeah, big amount of papers were identified and scanned. I managed to find some trends of interest in the last 10 years. And the classification that was done for the decision types contains 40 consensus algorithms, while at the same time, the second classification based on the access contains 35 algorithms. Honestly, there are many more algorithms, but yeah, throughout the papers, throughout the research papers, I managed to identify only those, and that's the reason I put only this amount of consensus algorithms. So with that, I finish my overview. You see my contacts on the slide, and thank you very much for your attention. Any questions? Hello?
Yes, you have done a wonderful job. I mean, it will be helpful for those who are working on this particular field. Thank you.
Thank you very much for this feedback. Thanks.
Thank you so much. And I sincerely thank our authors for their excellent presentation and contribution in this session. We have completed all the presentations, and also for being a part of this international conference. Thank you so much, everyone. I hope this session was informative enough, and we on behalf of whole team thank you for your support in this version and the previous version. We will be happy to have you in the next version of this conference, which is the 7th version in 2023. All the presenter would be getting digital certificates through email within 2 working days, and further all the papers are already forwarded to the Springer, and the publication will be live within 5 to 6 months. So kindly be cooperate with the team of WS4. And thank you so much, sir. I would like to thank our chair of this session, Professor Shamim Kaiser. Thank you so much, sir, for being a part of this conference and for your valuable time and presence.
Thank you, Richa.
And
I gladly accept this one. Thank you.
Thank you so much, sir. And I would like to ask everyone, please turn on the cameras for taking a quick snapshot. Thank you so much, everyone. Thank you, sir.
Thank you, everyone.
Thank you. Thank
Bye.
you so much. See you, King. Bye.